Hey everyone, and welcome to this explainer. Today we're taking a massive deep dive into the high-performance engines driving modern dermatology AI. We aren't just looking at what these systems do, but exactly how they do it. We're going to literally tear down the architectural blueprints, look at the actual performance metrics, and figure out how the smartest computer vision models are learning to spot skin cancer. But, to really understand this solution, we first have to ask a pretty critical question. Why do standard AI models struggle so much with skin cancer? Because for years, standard black box models in medical computer vision have had this, literal fatal flaw. They might score super well in a controlled, pristine lab, but they fail out in the real world because they just get easily confused. Okay, let's dive into this. The root of the whole problem is noise. When a trained dermatologist looks at a clinical image, they just instantly tune out all those background distractions, right? But a standard AI, it looks at absolutely everything equally. It gets distracted by hair and normal variations in skin texture. It sees surgical ink markings and actually thinks they're part of the disease. It even looks at the little millimeter calibration marks on a medical ruler and creates spurious correlations, literally thinking the ruler itself is a sign of cancer. Combine that with weird lighting and camera lens variations, and you end up with an algorithm that just generates incredibly high false positive rates. So, here's our roadmap for today. First, isolating lesions with deep UNet. Second, mastering focus with attention mechanisms. Third, measuring success through ablation studies. And finally, explainable AI in practice. All right, section 1, isolating lesions with deep UNet. Let's start with the first major architectural innovation. Before an AI can even attempt to diagnose a lesion, it has to accurately find it and clean up all that noisy image data we just talked about. Enter Deep UNet. Honestly, in plain English, you can just think of Deep UNet as an incredibly smart, automated cropping tool. It uses two really key components. First, dual attention gates. These actively highlight the important lesion regions while totally suppressing the noisy background. Second, Atrius spatial pyramid pooling. Now that sounds like a mouthful, I know, but essentially it just allows the network to capture context at multiple different scales, meaning it can recognize both tiny pinpoint melanomas and massive sprawling lesions without ever losing resolution. And the proof is really in the data here. On the benchmark ISIC 2018 dataset, this deep UNet architecture achieves a massive 91.17% MDI score. Now the MDI score is simply a metric of how perfectly the AI segmented boundary overlaps with a human expert's boundary. Achieving over 91%, that basically proves this engine is incredibly efficient at stripping away all the noise. Moving right along to section 2, mastering focus with attention. So now that we've got a perfectly clean, isolated image of the lesion, we can actually move to the next step, which is feeding it into the classification engine. And this is where the architecture gets truly fascinating. Modern state-of-the-art models don't just use one neural network anymore. They actually use a dual network approach. Step 1, as we just saw, is segmenting the lesion. Step 2 utilizes two parallel DenseNet 201 encoders. Basically, one encoder looks at the raw, original image to gather global context. The second encoder looks only at our clean, cropped lesion. Finally, in step 3, a multi-head cross-attention mechanism actually fuses these two visual streams together. The researchers describe this fusion beautifully. They state that it's forcing the network to balance contextual background information with precise, localized lesion morphology. I kind of think of it like a seasoned medical specialist. When an ER doctor walks into a chaotic, noisy emergency room, they obviously use the context of the room, right? But their internal attention mechanism tunes out the noise so they can focus exclusively on the patient's critical symptoms. The AI is now mimicking this exact human clinical behavior. Okay, section 3, measuring success via ablation studies. We've seen the architectural blueprints. Now it's time to put this AI engine on the dyno, so to speak, and test its true horsepower. In machine learning, we test that horsepower using an ablation study. If you're not familiar, this is just the scientific process of systematically stripping away or adding specific components of the AI model. By doing this, we can mathematically measure the exact performance contribution of each individual piece. It proves beyond a doubt that our architectural innovations are actually doing the heavy lifting. Now, what's really interesting about this is watching how these incremental victories break down. We start with a powerful baseline model, the efficient net V2L, which hits a really impressive 89.20% accuracy on the dataset. But watch what happens when we stack our optimizations. We add channel attention, and boom, we gain 0.8%. We add smart data balancing, which synthetically oversamples rare lesions so the AI doesn't just lazily skew toward common moles, and we gain another 0.6%. Finally, we add progressive training, yielding another 0.55%. In the high-stakes world of medical AI, every single fraction of a percent is a hard-won victory that could literally represent thousands of accurate real-world diagnoses. It's really clear to see how the accuracy climbs here. Sequentially stacking these components does something absolutely crucial. It mitigates what computer scientists call catastrophic forgetting. That's where an AI learns a new pattern but completely forgets an old one. By integrating attention mechanisms, data balancing, and structured training all together, we squeeze every last drop of diagnostic optimization out of the model, bringing us to a remarkably robust 91.15%. Which brings us to Section 4, Explainable AI in Practice. Here is the ultimate reality check. A high accuracy score on a chart doesn't matter at all if a doctor sitting in a clinic cannot trust the AI's reasoning. Accuracy has to be paired with transparency. So this is exactly where GradCam comes in. It stands for Gradient-Weighted Class Activation Mapping. Think of GradCam as our flashlight inside the AI's black box. It generates these visual heat maps over the original image, showing us exactly which pixels strongly influence the AI to make its prediction. It essentially proves how the AI makes its decisions, not just what decision it made. And this brilliantly illustrates the difference. With a standard AI, the heat map is incredibly diffuse. It's glowing all over the place. It's looking at the medical ruler, it's tracking skin hair, it's just totally distracted by image artifacts. It might guess the right answer, sure, but for completely the wrong reasons. But with an optimized, explainable AI, the activation heat map is tightly concentrated directly on the lesion's core morphology. It is looking exactly where a human doctor would look. No distractions. That level of visibility is how you actually earn clinical trust. You eliminate the black box opacity. You mathematically validate that the AI is using relevant pathological features. And on top of that, modern architectures can integrate patient metadata, stuff like age, sex, and where the lesion is located on the body, directly into a transformer module, fusing it with the visual data. The whole shebang works together to drastically reduce false positives in real-world clinics. However, we really have to remain grounded here. There is still a massive hurdle called the diagnostic translation gap. Even models that hit 95% accuracy in controlled lab environments see massive performance drops when they hit the diverse, unpredictable realities of an actual clinic. Just think about the variations in camera hardware, unpredictable room lighting, and completely different photographic angles across thousands of offices. Building a great architecture is really only step one. Validating that performance across a truly heterogeneous clinical environment is the ongoing battle. But the architecture is evolving incredibly fast, moving from academic theory straight to FDA-cleared devices operating in primary care. As the leaders in this field envision a world where skin cancer assessments become as common and everyday as checking a smartwatch ECG, the ultimate question remains, will we actually trust the algorithms making the call? Well, thanks to these explainable attention models, I think we're getting a lot closer to a definitive yes. Thanks so much for joining me on this explainer, and keep questioning the algorithms.